Okay, so this is what we're going to be doing today, is the question is going to tell you how it's being stressed. Sorry. Right? So the question will tell you, I'm going to add more beans, or I'm going to add more noodles, or I'm going to take some away. Your job is to tell me how it's going to fix itself. What is it going to do to balance it back out? Okay? And really your answers today are going to be like one of three things. It's either going to mean it's going to shift left, shift right, or nothing. Another thing you could do with what we're doing today is we can say left and right, but actually on your assignment, you can actually draw mostly arrows, and you can just draw an arrow pointing one way, an arrow pointing the other way, right? Instead of writing left and right, it's fine too. Okay. All right, so let's start with concentration, which is amount. So with our analogy here, okay, so let's say I'm going to increase my reactant. So this is my reactant container, okay? So this is the stress, ready? I'll give you a second to fill in your blanks so you can put your eyes up here. All right, before I move on to, you need to fix something for me. So where you just filled in, there's a bolded word that says example. Do you see that? Mm-hmm. And then next to example, it says decrease. That should be the word increase. So right by example. Okay, so the stress that I'm applying is I'm increasing a reactant. Okay, so this is the stress. I'm choosing to add more beans. Okay, so as a result, I added more reactants, so originally the scale is stressed, like this. Now what you guys want to figure out is, okay, the system needs to fix itself on its own. It can't just get rid of things, and it can't make something from nothing, because those are the laws of chemistry. So what can this system do? This is really like one beaker. What can this system do so that it's balanced again?
Balance out the products.
How would it do that?
Add more products.
How?
Since you added more reactants, it makes more products, so you can just add more products.
So it's adding more product by changing the beans into noodles. Because it can't just add noodles from nothing, right? So this is our reaction, okay?
But you just added beans.
So I chose to add beans, right? Now the system wants to rebalance itself. So the system says, okay, I'm going to move some of these over here to make it level again. Okay? Don't worry, we'll walk through this step by step. Ready? So add these arrows in next to your example. So the stress that we're doing is this. This is our stress arrow. So draw an up arrow underneath your SO2. This is the thing we made happen. Now what we want to do is figure out what is the system going to do to rebalance itself, okay? So if I add more to this side so my scale gets tipped heavy one way, I need to shift to the products or to the right side, so draw an arrow shifting to the right to rebalance it, right? Basically, you're always going to shift to whichever side is lacking because it needs more of it. So if I'm shifting to the product side, what's happening to the amount of my noodles? What happened to those? I got more noodles, and what about the beans? Less beans. So in terms of amounts, these went down, and this went up after I applied this stress. Okay? All right, we'll do some more examples here. Okay, so another way we could say it is that the forward reaction is favored. Okay, what that means is that more products are being made. It's just another way of saying it, that the forward reaction is favored. So we can say that it's shifting to the products, that it's shifting to the right, or that the forward reaction is favored. It's another way of saying it. So if we break it down, the SO2 and the O2 concentration are increasing, then it's always going to shift to the right because I've made this side heavy, and so it needs to shift away from the side I added it to. In general, anytime you add something, it's always going to shift the opposite direction because you already have too much on that side, right? And in a sense, then it gets used up in the process. So let's define this a little bit more. So can somebody help us out? What does it mean when I say it's shifting right? What does that mean is happening? Mitchell, what do you think?
The reactants are going to products.
Perfect. It just means the reactants are changing into products, or it's going in that direction. Okay? So what we've achieved is we've achieved a new equilibrium. Okay? It can't be the same because I added more beans, right? You can never get back to that same as it was, but the thing is, like Jace brought up at the beginning, is that the ratio is maintained. In the end, if my beans could actually magically turn to noodles, in order for the scale to be balanced, is the ratio maintained? Yeah, it has to be, right? So the ratio is not the same, but we have reached a new equilibrium because there's more in there than there was before. All right, let's just do a quick self-check. Take this as a little mini quiz. On the top of page 8, answer questions 1 and 2 for me.
Except I like took it out from my styles and stuff.
Nope. Tension back up here, everyone. All right, so now let's talk about what happens if I decrease it. Okay? So now what we're going to do is the stress we're going to apply is I'm going to decrease some of my product, or I'm going to remove it. Okay? So that's the stress. So if I remove some of my noodles.
There's still beans in there with the noodles?
Yeah, but okay, so if this is the stress, right? There it goes. It goes up a little bit. So I removed some of my product. So just point with your finger for me. Which way does the reaction need to shift to regain balance? So my scale's like this. Which way would it go to rebalance? There we go. It needs to go to the side that doesn't have enough. So it's going to go this way. So whenever I remove something, guys, it needs to make more of it, right? So the shift actually will be back towards it. Yep, to the right in this case. So when you add, it goes the other direction. When you remove, it goes back towards it. Okay? All right, so then tell me this, everyone. Ready? Focus back up front. So if I'm shifting this way, what's going to happen to the amount of my noodles on its own right now? It's going to go back up, right? So we're going to get more noodles because the beans are going to turn into noodles. Kind of. We'll do another example here. Okay, so the forward reaction is also favored if it's decreased. So if I decrease, it also goes to the right in the end.
Oh, it's just to the left, right?
Right. Yep, shift to the right. Okay, so these are all the different examples we could have. It's going to shift to the right if concentration increases in the reactants, or if the products decrease. It will shift to the left if the reverse happens. Okay? So once again, I don't encourage you to like memorize these things. More if you understand how Le Chatelier's principle works, you can answer any question about it. Okay? So for example, let's try this one. In this example up above, if I add more SO2, fill in that blank for me. Which way is it going to shift?
Is this on our paper?
Yeah, this is on your paper. It's where it says example,
So
and then underneath that.
If she adds SO2.
It's on her paper.
If you add SO2.
Your paper. You add SO2, just there's a blank, so write left or right on that blank. Then point with your finger for me what's going to happen. So which way is it going to shift? And don't point at the ceiling. That doesn't make any sense. Good. It's going to shift this way, right? Because if I add more here, originally it gets heavy. So remember, you're not answering how the scale tips. You're answering how it balances itself out, right? So it needs to balance out by shifting that way. Good. One thing to be aware of as we're looking at these problems today that you're going to start seeing is you'll start seeing things with brackets around it, which just mean concentration. Yeah, right there. Didn't I point? Didn't we say right? It is right.
So it's
You're
basically
right.
going, whichever side has less, it needs to get more of, it needs to get more of that to go that side.
Exactly.
But if, like, that side has less, it needs more of that to do that way.
Yep. Yeah. Perfect. Okay, so here's one thing you got to be really careful with, because I don't want you to get tricked on the test. Okay? Is if something in your balanced equation is a solid or a liquid, it has no effect on the change. The reason being, solids and liquids don't change in concentration. It's already 100% concentrated if it's a solid. Okay? So when you look at a balanced equation, so look at this one, everyone, eyes up here with me. So if this was my balanced equation, and the question said I'm adding more O2, your answer would be no change, no shift. Why this time?
Because it doesn't change the concentration.
Because it's a pure liquid, so it doesn't affect it. So what you need to start paying attention to are these little symbols next to them. If it's an S or an L, no change. The two things that will change are gases, and then, does anyone remember the other one you'll sometimes see? There you go, yeah, you'll see aqueous. It's written as AQ, so if you see like...
What is aqueous again?
You're right.
It means it's dissolved in water. So this is like salt water, which is different than like liquid salt. So just be careful that when you see an S or a little L, that there's going to be no change in the equilibrium. You're putting more in, yeah, that's happening. But in a sense, it's like putting in beans that don't cause it to get disrupted.
So like liquid won't change if the liquid doesn't change.
Pure liquids and pure solids, no change.
So if it is salt water, though, it would change because it's not pure
Yes,
liquid.
because it's not a pure liquid. Yeah.
Pure water.
So anytime you see like AQ next to it, it will change it.
Okay.
Yeah, very good. All right, let's try a few more practice problems. Answer 3 through 7 on your own, A, B, or C, and then we'll check it and see how we're doing, right?
What equation is this going to?
Oh, that's up here on the board.
Oh.
Yeah, you want to look up on the board for the balanced equation. I should have typed it on your notes.
Did it?
Dutch. All right, so skip all the pressure section and go to temperature. All right. Okay, so the trick with temperature, everyone, is if concentration changes makes sense to you, like if what we did so far, you're like, okay, I feel good about this, then the best way to think about temperature is we're going to treat heat as a product or as a reactant, and that's going to be dependent upon if it's exo or endothermic. So the first thing we need to review is how we know whether a reaction is exo or endothermic is going to be key here, because it will change depending on the type of reaction that it is, okay? So if the temperature is decreased, then the reaction will shift in favor of the reaction that will release the heat, and an exothermic reaction is favored. All right, so don't say it out loud, but for this example, fill in that line, that blank. Is this an exo or an endo reaction? Don't say it out loud, but fill in that blank. Is this reaction exo or endo? And this is something you should be able to do for the test.
How do you release negative heat?
Okay, so that's the difference, right? So what does the triangle H mean again?
Rate of
Change in heat, okay? Change in heat. So if the change in heat is negative, it's because the products have less energy than the reactants do. Because change, it's just a directional thing. When it's in the equation like it is on your paper, it's never going to be negative because just like Mitchell said, energy can't be negative. But it's going to be written on one side or the other.
So if it's on the product side, it's going to be exo?
Yes. So if it's on the product side, we know it's going to be exothermic. Okay? So then, knowing that, if we can say energy is a product, and then if I increase the temperature, so ready? Follow this. So if energy is a product, it's on this side, right? Only because it's this reaction, right? It could be different. If I increase heat, the product side, in a sense, gets too heavy because that's where the heat is. So which way does it need to shift?
Left.
To the left. So the tricky thing with temperatures, you have to figure out what side the heat is on, so then you can answer it appropriately.
So whatever side the heat is on, it's gonna be.
Well, if we increase it, then yeah.
Oh,
Really, once you figure out what side the heat is on, you can do these exactly the same as we did all the others. All right, so this slide right here isn't on your paper, but these are, maybe this will clarify, these are all the different ways you could see exo or endo. All of the pink ones are exothermic examples. All of the blue ones are endothermic. Okay, so a problem could either say delta H equals something. In that case, you're looking for negative or positive. Or it could be written in the equation, and in that case, you're looking for where it's at. Is it on the product side, or is it on the reactant side? Okay, so these are just the different examples you could see of if it's endo or exo.
So pink's exo?
Yep, so in this case, all of these ones are exo if it's pink, and all the blue ones are endo. Okay? All right, so for our last practice problem together, answer these 3 questions. You don't have to. That's more for what we're going to see. So the cool thing about this chemical reaction that we're going to practice as well as graph, and we'll see, is a lot of times with equilibriums, you can't see anything happen because it's happening at such a small level, and going back and forth to us, it's like nothing, right? It's like the whole analogy of like if you're up in an airplane, the cars often look like they're not even moving. But the cool thing about this equilibrium is depending on which way it's shifted, it actually is different colors, so we can see it. So when it's shifted to the reactant side, it is pink. When it shifts to the product side, it turns blue. So this side is more reactant favored right now, and this is more product favored. So what we can do is as we actually cause these stresses is we can visually see it changing. Okay? So draw a graph underneath or a line for your graph. This is our ICANN 9.5b. The y-axis of our graph represents the concentration. And then the x-axis of our graph will represent the different stresses that are happening. Now I'm going to mostly use different colors. I'm running low on my colored markers. I'm getting to one soon, but I don't have them yet. So I'm going to have to repeat one of them. So if you have different colors to use, you can. Otherwise, make sure you just label your different lines. Okay? So before I do anything, it's at equilibrium. So how do equilibrium graphs look?
oh, did I
Stop.
Good. Eventually, we're at the point they're flat, right? Because I'm already at equilibrium. Okay, so my black marker, I'm just going to do them in order. So this will be CO. Okay. My green marker will be my Cl minus. Brown marker. And then H2O. Okay? So if you don't have different colors, just make sure you label your different lines like I did. So the first stress that we're going to do, so right here at this point in time, is we're going to add some Cl minus to our reaction. Okay? Now the first thing we want to answer, just like we've been doing the whole time, is the main shift. So if I add Cl minus, point with your finger the direction that the reaction will shift. Don't say it out loud, but point with your finger. If I add Cl minus, which way should it shift? Good. So if I add Cl minus, it's shifting to the products. So we should see this turn blue. That down for a second. Now, I'll hold it up in the air as I do this. If you watch really closely, you can actually see like the states of it shifting, because it'll take a few drops at a time. So in the beginning, you should see it start to change. And then as it gets closer, we'll get an in-between state. So it's kind of getting purple. It's kind of cool because you can see the blue hit, but then it kind of goes away because it's not there yet. Is that kind of purplish? And then make it a little more blue. And then we can shift it to the product side. Now, when you graph equilibriums, the first thing on our graph we're going to show is the shift that we did, or the stress that we did, as I should say. So the thing that we did was we added Cl minus. So when you add something, that line is going to have a vertical spike up, because I made it go up. So right here on Cl's line, draw a vertical line going up. Okay. Now the rest of the lines is we need to write and show what the system does to fix itself. So we shifted to the blue, so that means everything on the blue has increased in concentration. So these two lines are going to go up, but it's a gradual up because that's the system shifting. And everything on the pink side is going to go gradually down. Now with these graphs, it's not about how far up or how far down you go. It's all about if you go up or down, right? They're not qualitative, meaning we can't have like exact, like you need more data to know how far up or down it goes. Okay? All right, stress number 2. We're going to add some H2O. So looking at our chemical reaction up there, if I add H2O, first question is which way does it shift? Point with your finger. Be careful that you pay attention to where H2O is. Would you drink that? Is that H2O? It has an H2O in it, but that's not H2O. It has H's and O's in it, but it's not H2O. Good, so it's shifting that way. Okay, so what happens to my graph because I added it? Good, so we need H2O spike up.
Blue goes gradually.
Good, so now we're shifting away from blue and towards pink. So all the blue things go down. And all the pink side should go up. Now, obviously, it would be silly to add water to something that's already pink because we're trying to see it shift. So I'm going to add it to the one we just made. Where's my water? So here's our distilled water. Now, this one is kind of cool because their densities are a little bit different. If I add it, so you can see it starting to shift because the top of it has shifted. The bottom hasn't.
Looks like a popsicle from here.
A popsicle. And then it shifts up. Shifts back to pink. The cool thing about this reminds me of I'm going to say the wrong movie again, Sleeping Beauty. And how the fairies, like, the whole time are, like, fighting over her dress, if you've seen the old school cartoon. Right? Like, you can literally do this all day long with equilibriums. Like, you can change a blue and then to pink, and blue and pink. Like, equilibriums will just continue to shift all day long. Okay, the next stress is we're going to remove Cl minus. Now, what do you think happens to the graph if I remove something? Adding was a spike up, so removing would be spike down. So on the line for Cl, so Cl is my green one. So this is the one I'm removing, so initially, jump down. Now to fix itself, which way is it shifting? Good, so chlorine's on the left. Since I removed it, it's shifting back towards it. So we're shifting back to pink, so everything on the pink side goes up. Everything on the blue side goes down. Now, removing a substance is kind of interesting in like practicality. So we're shifting, we're moving back to pink. So if I take my blue one here, removing something, once again, it's kind of interesting because it's like, well, how do you go in there and pull out the chlorine? So there's a few different ways. The ways we're going to do it is I'm going to remove it by putting something else that it will react with. So chlorine will react with the silver nitrate and become a solid. And then by becoming a solid, it comes out of the solution. So you're going to see two things in this test tube. You're going to see the solid be made, which is a white powder, but then we should see it also turn back to pink. So that's why this one's going to look a little bit different, is because there's kind of two steps happening here. So I'll do a little bit at a time so you can kind of see. So that white powder, is it pulling it out? But then you can see it's kind of like strawberry-like milk. And then there's our, as we let it sit, the powder will fall down to the bottom, and then the top would be just our clear pink solution like it was before. So that's kind of how we can remove it.
So how did you add heat to that?
That was removing Cl. Okay? All right, now let's add some heat. Now with adding heat, shoot, I forgot to turn this on. It's probably a little warm from last period still, but it may not work right away. First off, I look at the chemical reaction. If I add heat, which way is it shifting? Good, because it's endothermic, so heat's over there. So if I add it, it's going to shift the other way. Now, on your graph, what's different about heat is you're not going to have any spikes because it's all gradual, right? There's nothing you're adding or removing. It's only the system causing the shift. So since I'm shifting to blue, our two blue lines should go up. I lost all my markers. Where did I set them down? Yeah. Am I crazy?
Right there. It's on the board.
Oh, they're all there. I thought I put one of that. Thanks. And then all the pink lines, or the reactant side, will gradually decrease. So biggest thing on graphing with temperature is it's not going to be a sharp change. They're all gradual changes. Now, it'll take a little while, so I'll stick it in there so it can start going. So we're shifting to blue. So I'll stick this one. This water's heating up, so it's not going to happen super right away, but we'll kind of let it go. Obviously, we can predict if we remove heat, then what's going to happen? The reverse, right? It's going to go back to pink, and we'll create more of the pink and less of the blue. So you can add that one to your graph because it's just the opposite. Now, pull out for me, so in your assignment packet are 2 remaining papers if you've turned everything else in.